Hey
Hey guys,
guys,
it's Drusilla here or Drew,
and Olivia,
and
and
we
we
are
are
dope.
dope.
You might be wondering, what does dope stand for? Well, my name starts with a D,
And mine starts with an O.
and that's why we're dope. Where does the P come from? We
We
don't
don't
know,
know.
but that doesn't matter. And you probably don't care because you're trying to study for your OCHEM exams. Let's just get right into it.
Yes. Okay, so this is the 2022 um test from Dr. Berg's class. And as she said, we're gonna get right into it. So the first list of questions is nomenclature. This is where you want to get all your points, 100%. Just bang, bang, bang it out. Okay, so let's get right into it. First thing that we want to identify is our parent group, parent chain, Majiggy Mabob. So as we learned recently in class, we have these substitutive naming. So let's identify what our parent chain is. So we have our substituents, a methyl group and a bromine group. We know that our group is going to be this one right here, and this is toluene.
Toluene.
Alrighty, so if we follow the same format of naming, we'll start where our parent chain is. So we'll start numbering from the one and then go around straight to the bromine 5, 6. And in that case, this is going to be called 2 bromo. No space, no dash, no nothing.
No, nothing.
Toluene.
Spell it right.
Spell it right, or else you're not going to get the point.
No, very good.
Moving right along. We have another BR group, and then we have a CN group. I don't know.
I think BR is the substantive naming group, is it?
Unfortunately, you are wrong. The actual name here would be benzonitrile. So
Oh.
let's go ahead. It's okay. We all make mistakes, but
Mm-mm.
on the OCHEM exam, you're not going to
Don't
do
do
that
that.
because that's not allowed. And again, we're going to follow that same pattern. We're going to start numbering at our nitrile group right here. 3, 4, 5, 6.
So what have you noticed? That functional group will always get the number one. Don't
Number
have your
one.
benzonitrile and give it a three. That's not nice
Like
to her. Give her the one every time.
every single time because she's number you the one that okay, so in that case, where is our bromo group? It's at the 3 position. So we're gonna give her that 3. Bromo. Again, no space, no dash, no nothing.
Right on into
Benzo.
it.
Because remember, this is a benzene thingy-majug, but it has that nitrile
Okay.
group on it. So, okay,
Okay.
benzonitrile, exactly.
That's just the name of it. You don't need to complicate it.
Okay,
Mm.
again, let's do it again. Now we got a whole bunch of things, but I don't know. Do any of these have any like special thing going on with her?
Maybe the F?
Oh
No.
no. I think this is
They're
just a regular thingy. Yeah, it's just
benzene.
a benzene, man. So this would be our parent chain, and we're just gonna number and name as per usual, like we did last semester. Um, but the
No
only thing,
cyclobenzene, though.
yeah,
This is
not
just called a benzene.
is
Not
she
a
just a
cyclobenzene.
benzene. Let's
Benzene is
not
always
do
going
too
to tell her that
much.
she's a cyclo because benzene
She's
is
on,
cyclo.
that's intuitive. So basically, we're gonna again just number with the lowest numbering scheme. And so we can number from multiple different ways, but obviously we want the lowest one right. So we can start over here, and we can even start over here. But in all reality, we want the lowest numbering scheme and the most alphabetical of alphabeticals. Okay, so red is
Precisely.
green because basically you, as I said, you want to give the lowest number to the like earliest in the alphabet essentially. And so our bromo can either be at that 2 bromo or 3 bromo position. So that's why we're going to go ahead with the green numbering scheme. So in that case, we have 2 bromo, 1 for dichloro, because we got 2 of
So does
them.
the D matter here? Is that why we're putting that before the F?
No, it does not,
Why
Miss Ma'am.
not?
The die or the prefix actually doesn't contribute to our naming. And this is also something that you learned in OCHEM 1. So this is just like, refreshing.
Review.
Yeah, exactly. And then we can't forget about that fluoro. And also make sure you spell fluoro right
It's
because
not FLO.
mm, it's
Don't forget
not.
the U.
Don't forget the U. F L U O R O Benzene, because that's what we said our majiggy is. All right. Next, we have this majiggy.
Your
We got
majiggy.
this group. Oh, I wasn't no, I'm not gonna say that. That's not it. We got the no group and we got the CH3 group. Which one on our list of priorities is gonna go first? Well, I'm just gonna go
Is
right
it
ahead and
toluene?
no.
Why not?
Because CH3, she never really matters for real, for real. Like
Because
she
OH is
the
more.
most of the mostest. The O, not the no. So
No.
basically, yeah. So that's what
Because OH
our
is higher on the
the
priority
priority
of functional
list.
groups.
And you can even see it up here.
Hmm.
He should have that on the test. At this point in
But
time, February
we don't know.
11th, 10:14 p.m. and counting. We don't know if it's going to be on the test, but we can assume at said.
But memorize it
But memorize it
regardless.
just
You
in
never
case,
know.
because
It's a different year. They're doing it all together now.
yeah, together. So, but as you can see here, our OH is higher priority than our CH3 group. So that's who our parent is gonna be. So we're gonna have oop, a her and a her. Oh, I don't like that it's the same color. Let me redo that. Oh my gosh, wait, why has this been here the
Yeah.
whole time? Anyway, okay. We're gonna use pink. Bang, 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 bang. And so with that numbering and lettering and everything, how are we gonna therefore number? Again, we're starting right at that OH group. Never go do anything else. But now we're gonna which way do we go? Do we go 1, 2 over it this way or 1, 2 over it that way? Well, we're gonna
Alphabet.
yeah. Thank you. Good job. So
Wow.
we're gonna go bang, 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 because
Why is that again?
this is a methyl MMM and this is a nitro NNN. So obviously, you guys know the alphabet by now. So how do we name that? Well, our methyl is at the 3 position, so it's 3 methyl. Our nitro is at the 5 position, so it's 5 nitro. And what is our parent chain? Exactly. Thank you
Phenol.
very much. Phenol. Okay. Last one. So, what in the world do we have here?
I don't even freaking know.
Well, I'm just gonna tell you. This is called a thiophene.
And you should know that because
You
you should
should,
have already used Austin's flashcards.
yeah, or something, and or even your own. But alas, this is just who she is. Like you can't even get around. I don't know if you guys have
Austin
like
and Harper. Sorry, Harper. I'm sorry.
yeah. But yeah, so as we were saying, that's she's a thiophene. You should know that. And so we're just gonna again just number as per usual, starting at that S group this time. So
So
we
she
have
gets that one.
she gets that one because she's the one that I think about all day. 3, 4, 5. And so where is our bromo? Our bromo's at the 2 position, so it's 2 bromo thiophene. And just like that, you're done with your naming. And again, 100 points right there. So now
Period.
let's go on. We're gonna continue practicing this type of naming and the IUPAC and the common name and the right.
Already.
So what is this? 3, 2, 1.
Payroll.
Pyro. How do we? Well, yeah, you can pronounce it whichever way you'd like.
Yeah.
Um,
Spell it right. It's not one R.
is two. How do you know it's a pyro? Well, the way that we did it, usually like it's drawn with that what's it called? There
Lone
are
pair.
lone pairs right there. It's just like those two little dots is like the what's it called? The icing on the pie. Remember we
Okay.
said that.
Yeah, then the pie roll.
Pyro.
Get it?
Yeah.
Why
Okay.
not?
This one, ooh, I love okay, what is this?
Isoquinoline.
Isoquinoline. Iso for you basketball lovers out there.
Don't get it. You didn't
Okay,
spell it right.
I didn't.
Isoquolinine. Quinn.
No line.
Where's your dots?
I do the dot at the end,
Oh,
the
you're
much dot.
so.
Anyway, how do we remember this? I couldn't tell you, just know. ISO, because she's like ISO on the side, like ISO, like okay. Next, Ooh, she gonna get you. But like these are one of the three that is like special,
Mm.
but
This one is macetylene because she's just so messy. She's everywhere. You know, the other
she's
one is like, what is it? O cresol, B cresol, whatever.
yeah,
They're
O
like cool,
Crystal
but
and
messy is she got
Xylene.
three
It's
TH3s around her. She's so
oh, I
messy.
didn't even spell that right. That's actually wait, oh wait, Xylene.
You did spell right.
I just did I forgot the
N-A. Okay, so my turn now.
yeah, it's actually your turn.
Alrighty. Hi guys, I'm Drusilla, and I actually did this aromaticity for my review session for Berg. So you want to check that out? That's cool too. We're gonna do this real quick though.
Mm.
So how do you do aromatic things? First, you look for a cyclic ring. Then you look for sp3 carbons. Then you draw on your lone pair. And then you do your Huckel number. Thank you. Is it even amount of double bonds?
Is it? No, it
What?
is an odd amount of double
Or
bonds.
is it dot? That's the questions. Like that's what we're asking
Oh,
them.
I thought
Right.
you were asking.
No, not at all. Sorry, this is really ugly, but you can hear what I'm saying, and it's also on the review section if you want to just go read that page. But this is a quick little review, so we can do every page, period. All right. So, aromatic, we already know want it to be planar, cyclic, all these things that I've written here, period. Um, and we're gonna go through it in this order so that it minimizes the amount of work that you have to do. I'm telling you this. This is a foolproof way of doing it, guys. Use my method, okay?
Mm,
All right, here we go. Number one. So look for cyclic rings. Is there an opening somewhere?
maybe right
Okay,
there?
no,
Okay.
there's no opening. Okay, it's cyclic. Next, sp3 carbons. Is there sp3 carbons, Olivia?
And who? In her?
Yeah.
Wait, is that one right there?
Yes.
I thought that's what you were asking first.
That's what I was. No, no, no,
The
not yet.
openings at
Oh, that's not an opening. Okay, SB3. If I'm asking, how do we know that's SB3? She has the double bonds around her, and if we do our little method, this is what Gavin taught me. Y'all don't know who Gavin is, but that doesn't matter. If I draw an H in here, right at this carbon, H, we're gonna go SP, SP1, SP2, SP3. That is an SP3 carbon right at that center. And usually that's where your SP3 carbons will be for these double rings. So always look in those internal carbons. So
mm.
already we know this is non-aromatic. What is the directions asking you? Make sure you read. It says to circle each of the compounds that can be aromatic. Did he ask you if it's anti-aromatic? No. Did he ask you to circle the ones that are non-aromatic? No. He said circle the ones that are aromatic. So you follow those directions. So this right here, this is our next one. Now, I
I'm
once
thinking
again on my
twice.
page, I did explain what anti-aromatic, non-aromatic, and aromatic are in the review session, but I'll put it again here. What is anti-aromatic? I'm gonna give you some surefire ways to know that's anti-aromatic. I don't know if I spelled that wrong. If I did, life goes on. Usually it's gonna have an even number of double bonds, and it's gonna have a 4N Huckel number. Those are my two surefire ways to know. Alrighty. So here we are. We have this next structure here. So let's go through my list. Because why? Because it's a surefire way every time. Next, look for a cyclic ring. Is this a cyclic ring? Yes. Is there open anywhere? No. No, ma'am. There's not. Next, look for sp3 carbons. Is there sp3 carbons somewhere?
Mhm.
Let's look at these ones. Is that sp3? No. Because why? There's a double one right there. That sp3? No. No. Yes. There's no sp3 carbons anywhere on this structure. So it's not non-aromatic. That's what we know for sure. But not just yet. We have to keep on going. Draw in your lone pair. Are there any things that need to be lone paired? No, everything is completely satisfied in this ring. Indeed, in this ring, yes. And then Huckel number. We're gonna look at if it has an even number of bonds, odd number of bonds, and then just do our 4N plus 2, or and then also 4N. All right, let's do it right now.
Where'd you get this from?
So here is this. We have our pi electrons. That's what we're looking at right now. So this is 1. This is going to have 2. So 2, 4, 6, 8, 10, 12. So
Mm.
right here, this has 12 pi electrons. So we're going to do our 4N plus 2 equals 12. Subtract 2, subtract 2. This is arithmetic. So do you
Algebra?
remember that? No, arithmetic. Thank you. Um, actually, I think you're right. Okay, this is going to be 5 halves. Is that a positive whole number? We know that's not arithmetic because of this Huckle number here, but is it, excuse me, is it anti-arithmetic?
Yeah.
Let's try it out. Why is that? First of all, if you remember back here, anti-arithmetic is usually going to have an even number of double bonds. So using my method, you would have already tried to count the number of double bonds. 1, 2, 3, 4, 5, 6. So that should give you a hint. Maybe she's anti-arithmetic. But don't just go off of that alone. Now let's try our Huckle number, 4n. So we know that our number of Pilot times is 12. We're going to put that into 4n. 4n equals 12. And you could already guess this because we already know our multiples of 4, and 12 is definitely one of them. So, yes, this is anti-arithmetic. But am I going to circle that?
No.
Why? Because he didn't ask you to. But on the exam, they might ask you to. So just keep that in mind
Yeah,
for
be prepared
future. Yes.
and read.
Read. Definitely read the directions, guys. Very important for all these exams, okay? Especially now that we have joint exams, okay? Alrighty. So let's do my surefire way once again. Look for a cyclic ring. Is this a cyclic ring? Is there opening anywhere?
No, there's
No.
opening.
Everything is closed. Closed system. Okay. Look for sp3 carbons. Is there any sp3 carbons anywhere? Yes,
right
there
there.
is.
Yeah.
That central internal carbon. What I tell you, it's usually those internal carbons. Always look there. But also look on the outside too. But it's usually always there. Okay. There we go. Right there. There's an H right there. Is that sp3? SP, SP1, SP2, SP3. Yes, indeed, she is. So what is that? Non-aromatic. Next. You see how I didn't have to do Huckle number? But this is why my way is surefire. You wouldn't even have to do math because you already have done my list. You don't have to do the math because you already know. You see? Surefire way, user. Okay, next. This beautiful guy. Look for a cyclic ring. Is it cyclic? Is there an opening somewhere?
No.
No. Is that O an opening?
No.
No, that's closed.
I thought it was about 2 weeks ago.
No. No, she didn't, guys. That's a joke. Okay. Look for sp3 carbons. Is there sp3 carbons? Ooh. Is there sp3 carbons anywhere?
Yeah.
Yeah. He made these too easy for y'all. It's a lot of sp3 carbons. That's not usually how it'll go on the exam.
Don't be
But
prepared.
right. So right there we have sp3 carbons. So we can assume this is non-aromatic. So basically, none of these are circled. Next.
Yeah.
Okay.
Ooh.
For the
Oh wait.
I didn't. Okay. For the following compounds, circle the one that reacts to. See, this time we need to read the directions. You see, if you would have glazed over this, you would have already think that you only have to do one thing, but you have to do two. So that's why you read. Circle the one that reacts the fastest to electrophilic aromatic acid substitution, and please make sure to read what he's asking you, because he might put there nucleophilic aromatic substitution, and you were thinking electrophilic, and you're now in a slump. Everything is wrong, or it's not wrong, but it's flipped. You circled instead of squared, and you squared instead of circled. And put a box around the one that reacts the slowest to electrophilic aromatic acid substitution. So what do we know about reacting slowest and fastest and whatnot? What I do know is that if we look at our list of directors, our strong activator, our weak activator list, that is going to usually tell you the fastness of your electrophilic aromatic substitution and exactly how it is written. As you go up your chart, you're going to be reacting faster for electrophilic aromatic substitution. Now, that's opposite for nucleophilic aromatic substitution. It's going to be opposite, meaning that as you go up, it's going to be reacting slower. I'll write that down for you. So reacts fastest to thing is going to be your strong activators. And put a box around the one that reacts slowest. That's going to be your weak deactivator.
Strong deactivator.
Reacts slowest. Oh, my fault. Strong deactivator.
I mean, actually, wait.
Yeah, it's right. That's right. Okay. Yeah. Okay. And then for SNAR, obviously it's gonna be the opposite. So it's gonna be, instead of having the fastest be your strong activator, it's gonna be fastest is gonna be your strong deactivator. And that just has something, it has to do with the lone pair. But if you want to know like the real chemistry, we can come to my office hours and I'll tell you. Thank you. This is for if you need fast. The exam is in 4 days. There's no time to. I'm just joking. Alrighty, so circle the one that reacts fastest to electrophilic aromatic substitution. So we're going to go through all of them and list if they're a strong activator, weak activator, whatever it is. Okay. So first we have this C double bond O attached to an O and then an R group. So if we look at our chart, would we think that that's a moderate activator? No. Make sure you read what we're looking at. That's not a moderate activator. It is indeed a moderate deactivator because we have a carbonyl group attached to an O attached to an R. I call it core. And so that is a moderate deactivator. I don't like red anymore. Oh, it's taking a long time. Okay. Next, we have this O attached to a C double bond O attached to an R. So now that we know that, O attached to a C double bond O carbonyl attached to an R. So that's going to be a moderate activator. Make sure you look. All right. Make sure you look at whatever is attached directly to the benzene ring because that will tell you if it's moderate activator or moderate deactivator. Don't get those messed up because you didn't look what was directly attached. Okay, next. Now we have an NH attached to a carbonyl attached to an R group. R group meaning that's CH3. What is that? Moderate activator. Alrighty. Hack that you might have not known. Since these two are the same thing, these are both moderate activators. How do we know which one's stronger? Remember what I said? As you go up that chart, that's stronger. It's giving you the exact order. What's the strongest activator? NH2. What's the strongest deactivator? NO2. Because it's written exactly as it's like the strongness of it is as it's written. Very sorry for that.
Yes.
So in this case, we know for circling the one that reacts the fastest, we're gonna want to have the most moderate activator. So as it's written on the chart, or have as you have it memorized in your brain also. So memorize the order too. Don't just know the group, memorize the order.
With flashcards.
Yes, that I have in my the group me. Okay. So we're gonna know that the NH is gonna be the fastest compared to the O. And you can kind of assume that too. Because if we go up here, okay, so yeah, so since in this case, hack if you don't have it memorized in the order, electrophilic aromatic substitution. Electrophilic, that means we want those electrons. We don't have any. We're looking for H's. We have H's over here, that's why they're really good activators. But compared to this and that, she has that H, so that makes her a better activator. If you didn't memorize it and you're really and you don't know what to do, that's how you can know for electrophilic aromatic substitution. Okay, next. Whew, reacts the slowest. Well, we already know that this is the slowest because both of those are activators and this is a moderate deactivator. So we're just gonna go ahead and square that in. Because why? Because that is what the directions said. It didn't say put a circle on the other one.
Did it say put
It
a
didn't
star?
say bold it. It didn't say star it. It said box it. All right, next. Circle the hydrogens that are most likely to be substituted by an electrophilic aromatic substitution reaction. So that's a C reaction, which is like the same thing we put up there. Okay, so for this, what we look at is our directing. So we're just gonna classify them. So we know that this R group is going to be a weak activator. How I would memorize it is weak activator is WA, and then the only things that are weak activators is A and AR, so it's war. So you have WAR and then WAAR. Both of that is war. You don't care, but I'm just letting you know. All right. Oh, that's so sassy. So that CH3 is an R group, and then we have an OCH3. So that's going to be a strong activator. Oh, why did I put R up there? So sorry. That's going to be a weak activator. Okay, so in terms of these two, which one is going to be more directing or more important here to determine what's going to be taken and what H is going to be substituted?
The OCH3.
The OCH3 indeed. So, excuse me. Since it's a strong activator, how is it gonna direct? Ortho, para, meta, or yeah, that I already said all three of them.
Oh, that was a question. It's gonna do orthopara.
All right. So this is the carbon that's here. That's the carbon. So what's ortho to that carbon? This guy, but she's already there. This hydrogen. I'm just gonna highlight it because we don't know the answer just yet. Oh, it's there. Ortho. And then what's paired to that? This one. Make sure you read, circle the hydrogens that are most likely to. It didn't ask for anything, it says most likely to. Is there anything holding this carbon back? This H back? No. Is
No.
there anything holding that H back?
No.
No. So we can circle both of those. Okay. Okay, next we have circle the hydrogens that are most likely to be substituted by an electrophilic. Same question, basically. All right, so Cl is dum ba da dum. Oh, we deactivator. CH3 is in our group, which is war, the activator. And then NO2, which is a strong deactivator. So of these three things, which is the best activator, which is the strongest? The weak activator. So she's going to direct. So both of these things actually are in the ortho position already, because we know that weak activators are still going to ortho pair direct. So they're already in the ortho positions. So all we have as an option is the pair position, which is over here. If you forgot and you're really like you really weren't paying attention when Bird was talking, or you didn't pay attention when Taluga or Sanders were talking, um, ortho, this is the position we're looking at right here. Then this is I'm gonna do the pointer. Here she
Yeah,
is.
she's
There we
right
go.
there. No.
No, didn't get her. There we go. This is the position we're in right now. Ortho, meta, middle, para, perpendicular. Make sense? Yay, hope it did. Next. Wow, we have this beautiful frost diagram. This was also in my page. So if you want to get a more in-depth thing of that, you can go in there. So what we're gonna go by doing first is create those orbitals. So we know this is a 5-ringed structure. So we're gonna have um it look like this. I kind of just like to have this written out at least, so it makes more sense to me. Um, and then there's going to be an orbital here, orbital here, orbital here, orbital here, and orbital here. Let's read the directions. Draw the relative energies. Yep. Frost circle. Label bonding, non-bonding, and or anti-bonding. So he's asking you to do everything. He didn't say only do one part. So these down here, only put the circle, are going to be our bonding orbitals. And then we have a nice, beautiful line that goes across. That's going to tell us that that is the non-bond, excuse me, non-bonding orbitals. And then we have our anti-bonding up here. Make sure you read the directions because you might have glazed over that and you already put your arrows and you thought you were done, but you're not done. Okay. And it says, show the electrons in the proper orbitals as paired arrows. There should be 5 pi electrons. So I'm gonna label those as well. Pi 1, pi 2, pi oops, 3, pi 4, pi 5. Okay, we're good. Okay, now we're gonna actually solve the problem. So in this, first we have to figure out is it aromatic or not aromatic. He already told us down here that it's aromatic, but now you have to figure out for yourself why it is that. So I'm using the cross diagram. So over here, did he put in the lone pair? No, he didn't, because he doesn't love us. He's joking. But he usually won't do that for you on the exam. So we're gonna go through my list, which is in my brain now, because you guys already have it in your brain now too. Yep, I thought so. Okay, first we're gonna look if it's closed. If it's closed, if it's cyclic, it's closed. Yes. Next. Excuse me. Next, we're gonna look and see if there's sp3 carbons. Is there sp3 carbons in this? No, there's not. Then we're gonna draw out one pair. Period. Right here and right here. Now we're gonna do our Huckel number. So this was the question, why is this number? So first you have to figure out the number of pi electrons. You might think that there's 8, but in this case, it's not 8, it's 6. Why is it 6? Because only one of these pair of electrons is contributing to the continual pi electrons in this delocal in like that are delocalized in that ring. If that makes sense. So only this is going to contribute to the. I'm trying to like, make it make sense. If you think about it, like we like for the benzene ring, oops, this is how it looked with like the dashes because they could just continuously move. They were all delocalized. They could move around. If you think about it that way, only the one that's like only one of those pi pair of electrons is going to be contributing to that. The one that's on the outside, he's not going to be. So there's 6 pi electrons in this case. Okay. So then we can do our Hookeland number for N plus 2 equals 6 minus 2, 4 to n equals 4 to n, oops, 4 n equals 1. That is indeed a positive whole number. So this is aromatic. Okay, so now we have now that we know we have 6 pi electrons, we're gonna start at the bonding orbitals, and you know you go level by level. So you put up, then you go down, then you go up, down, then you go, yeah, you get it. All right, so up. Is there another orbital there at the pi 1? Yes, down. The answer was no. There's no other
Or
but
oh,
orbital. That
the one
sorry,
that I asked that I
I
couldn't
know it was
choose.
really, so I'm sorry. Okay. Next we're gonna go up. Am I gonna go down now?
No.
We're gonna go up to the next guy.
Yeah.
Down, down. Are we at 6? That's 1, 2, 3, 4, 5, 6. We're done. That's it. Did it ask for anything else? Let's look and make sure. Draw the pi, I'll give it the orbital diagram. I'm gonna skip all that because that's all the same thing. Label bonding, we did that. Show the electrons in the proper orbitals as paired arrows. We did that. There should be 5 pi orbitals. We labeled that. In one sentence, why is this aromatic or what makes this a closed system? So we just finished all that. Now we're gonna say why it's aromatic. Why is it aromatic? All the electrons are paired in the bonding orbitals slash all bonding high molecular orbitals are filled. These are two separate ways you could explain it that both mean the same thing and are both acceptable answers. This first one is how I would describe it and would still be right. And then this is how Berg would describe it, which is perfectly fine as well. Next.
Now to what we also love. This is also a great place for getting some good points in. We have resonance structures. So we're just moving and shaking things and shaking and moving things. So what should we do first? Well, the first thing that I immediately see is a door hinge. Miss Thingy-Bob over here can just switch right on over to right here, and that'll end up looking like so. Bang, 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 and H2. Don't forget your lone pairs. We have a bond right here. And then, as we said, that will door hinge right here. But remember that there's a positive charge on this other carbon, and that will be your first resonance structure. Then, what do we see? Remember, there's delocalization in these electrons or in this structure. So we now know we already did that door hinge majiggy. We can see that there's lone pairs right here. So what can we do in that case? We're going to actually just make a double bond right here. So that will look like so, bang, 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 and H2. And we had a bond over here, a bond right here, and now we have a double bond. This and she don't really like that much, so she now has a formal charge.
Why? Because N likes to have 3 bonds and 1 lone pair.
Lone
So
pair,
you know if you don't
exactly.
see it like that, something is wrong. She's
Something's
not
that
happy no
you
more.
gotta add something else to her, okay? And that would be the positive formal charge. So now
Now,
let's
what's the question asking you?
yeah, what's the question asking me? It's asking me not to just draw these resonance structures, but also circle the one that contributes most to the hybrid. So out of these three, I'm gonna choose, well, you tell me which one.
Hmm. Is it the one with the most bonds?
Exactement. So the most bonds actually is this one right here. So that would be the one that contributes most to your hybrid structure. Next, we have a beautiful good old mechanism. And in this one, we have this structure called a furan, and it's being brominated. So she could be fairly simple I feel like Dr. Berg, he liked to do that one,
We
like
do
maybe he'll just,
fluorination, but it's all the
yeah,
same,
do one of the
really.
halogenation, maybe he'll
Um,
just be nice and just
but still know the
flip.
nitration, sulfonation, know all of those too.
Yeah, all of them will just be nice, like three heads mean three.
Alrighty.
Okay, so basically what happens first? We break bonds. So this bond right here is going to break, and I'm just choosing this one because in the final product it shows that our bond is over here, so I'm not going to choose this one. I'm going to choose this one. But so this bond is going to break, and it's going to go ahead and just grab right on.
Go ahead and won't you go
Go
ahead
ahead
and
and
go
just
ahead.
grab that bromine right there. Just
Hmm.
go ahead and grab
Go
that
ahead and just
bromine.
brom that.
Yeah.
Brom
And
that.
so, bro,
Brom that. I'm so sorry.
yeah,
Continue.
okay. And the electrons within that bond are going to go to the bromine. Um, and also remember, when you break bonds in this, you have to label what the rate determining step is. And in that case, it'll be the very first step, which I want to say like
It's,
9 times out of 10, it's going to be
but
that
don't
first
just
step.
assume that.
Don't
Why
assume.
do we know it's RDS? Because we break it a bond and that takes a lot of energy.
So now we have a structure that looks like so. Bang. Bang. Don't forget your lone pairs. We still have a bond right here, but now we have a bromine attached to our bond. I mean our structure. And then there's also just for visual sake, there's also an H over here as well. So now this carbon right here is deficient. So she has a positive formal charge on her. What else do we have just like floating around in the water? Well, we have our generic base B, and that's something that you guys will be able to use on your test. Don't worry about finding some mumbo jumbo unless you want to. But generic base B works perfectly fine. So we have her just floating around in the solution. She's right there if you didn't see her. But I don't like that. No, we're just gonna draw her in black actually. So yeah, we have her just floating around in solution. And obviously this structure, she's not very pretty. But before we continue on with that, another thing that you guys are gonna have to do in your mechanisms, do not forget it because your
Do not.
question is not complete without this because um as you can see, it says show all resonance structures formed. You're gonna want to show all resonance structures
Mhm.
formed. So before we continue on with our generic base B and doing all that thingamabobs, we're going to draw our resonance structure or structures. So our first resonance structure will look like so. We can see here that we have another door hinge, lovely thing right here. So this bond is going to go ahead and just flip right there. And we're going to redraw our structure like so. Bang, 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 bang into the room. And so our formal charge is not going to be over here, and our bond is going to be right there. We still have that bromine and that H. And we can do actually one more thing. She's not that pretty, but she still works. So we have one more resonance structure, and she is also going to look like so. Bang, bang, and we have that bond up there. We had our bromine right there, our H right here. And what do we see with that oxygen? Well, she has two pairs of lone pairs, two lone pairs, two lone pairs,
Two lone
two
pairs.
lone pairs. So we can actually just go ahead and form a double bond with that. And we'll have still like one of our lone pairs, but now this oxygen has a formal charge, a positive formal charge. So those are all the possible resonance structures that you can draw for that initial compound. But let's rewind and go back to our generic base B. So as I said, our generic base B is floating in water, and we have this H hanging around. We have this formal charge up in this, like, wait,
We don't swear in this area.
no. So basically that generic base B is gonna just go ahead and grab right onto that H. And then that those electrons within the H bond are just going to go ahead and reform that double bond that's in that furan. Okay, so then from there, and k- mind you, look at all of the arrows that I've drawn. We really like to pay attention to arrows in here. We have these double-headed arrows, but in this step, this is irreversible. And so it's only gonna be a single-headed arrow. Um, so yeah, we have this structure right here, with these double bonds formed right here as so. Don't forget your lone pairs, and that H is now gone. She's somewhere else for real. And our bromine is right here. What have I been missing? Let's take a gander. I don't have my lone pairs on the bromine in any of these. So just go ahead. You're not wrong if you're right. So just go ahead and draw all of your lone pairs into all of your bromines because they exist. So you can't just ignore her, you know? There we go. That's your final structure. You also just have your hydrated generic base B floating in water. And she looks like such, that's what she looks like being whatever. And then you also have um no, actually, you don't have anything else. That's just all you have. That's your final product, actually. So, this should also be a fairly good majiggy that you get on the test. I believe in you all, and we're just gonna go ahead and pass it right on.
Yay, it's me. Okay.
Hi. Um,
Okay. All right. Next we have synthesis. So, oh my gosh, this chair is really bad.
I don't know why you
I
keep
got it
leaning
from
back.
Amazon. I'm sorry. Okay. So this is a synthesis. Synthesis is hard. I can't lie, it is hard. Half of it comes from memorizing your reactions. I can't lie. If you don't know reactions, you don't know where to go. So if you don't know the reactions, I have a flashcard that I sent to the group me. If you need it, you can also email me. Um, yeah. So how do we do this? How do we synthesize this 1,5 chlorobenzene from bromobenzene? We can also look at the rules he gives us. Like if you are really like stuck, you don't know what to do with your life, he gives you a bunch of rules that by now should be applied in your head. Like it's just written out, but like you already know it. But he does write it out for you as well. Um, let's just begin now though, because there's no less talking, more doing. Okay, so now we have this bromobenzene. What do we do? What do we do? What do we do? First step. I always say, when in doubt, like when you really don't know what to do whatsoever, like even if we're looking at this structure right here, right? I would assume, okay, this is a Cl and a Cl. So I know that it's two and they're both in the ortho position. Like it could be both be in the ortho position compared to this spot right here. So I would think, I'm gonna definitely use a Cl2. And if I could use a Cl2, I would probably want to do it with a strong activator on it. Why would I want to do it with a strong activator on it? So that it can over-halogenate. We know that if we have strong activators that don't have a strong deactivator on as well, strong activators, they're going to over-halogenate because that's just their character. They're just like that. They always do too much. So that's what I would assume now. But how would I get something here so I could over-halogenate that and get a strong activator there? That's what we decide now. Okay, let's go. Let's try. Let's try. So what we know already is we want something to go here in this spot. We don't know why. But if we look at this structure, we know we can get something there. From what? Orthoparadirecting stuff. Like there we have
Yeah.
so many gosh darn options. But I always say if you're in doubt, you don't know what to do, just go ahead and go ahead and go ahead and just do a nitration. So Br, and we're gonna do HNO3 with H2SO4. So obviously this is gonna give us ortho and para as our product, but we're gonna only choose that para. Why? Because if we get a para, we can get an ortho. And then what I said in the beginning, please go back and listen to it again. If I kind of like saying it again, please go back. You can go back. You're watching a video. Okay. Alrighty. So HNO3, what I said is going to be ortho and it's going to be para. Ortho. It can either go here or it could go here. Br with an NO2 down here. It doesn't matter if you put a circle in it or if you put the bonds, as long as you indicate to me that it's a benzene and not a cyclohexane or cyclohex. Yeah, cyclohexane. Okay. So we know we have the ortho and para, but we knew that we only wanted the para position. Why? What I said before. Go back and listen to it. So we're gonna ignore the ortho. How can we ignore that? We filter it out because we're thinking about this as an actual organic chemistry. You can't just choose one and move on. That's not how that works. In actual organic chemistry, if there's like actually like we're trying to actually get this synthesized, this molecule synthesized, we're gonna have to filter it out because we're gonna have both of these options that occur. So we're gonna filter this. And I always make it clear and like indicate that I'm only going through with this para molecule, not the ortho one. Because if not, you'll have to go through and show all the steps you're doing for each of those structures. And I just feel
Yeah,
like
who
that's
wants to waste
who
time
wants to
doing
do that?
that?
No. So make it very clear that you're going through with only one of these things. If you don't, then you might get points off. So oopsies, filter. I'm gonna go through with this guy. So I draw an arrow from her only. Now we have an NO2 there. This is really good because now I know I can get an NO2 to an NH2, which is what? A strong activator, like how we wanted. Yes! That was so extra.
I didn't like
I
that
didn't
very
like it at all.
much.
That was like Teen Titans Go type of voice. Okay, BR. And we're gonna get that NO2 to an NH2. You see how that's really cute and stuff? Now we have a strong activator. And now we know when we have strong activators, what do? They over halogenate. Perfect. Now, it would be different if we had a strong activator here and then we had a strong deactivator on the other end. Then it wouldn't over halogenate. Then you'd be in a bit of a pickle, but we're not in a pickle. So let's move on. So we're gonna get this chlorinated. How we do that? Cl2 FeCl3. Yes, you need to know your base. Don't just put Cl2 there. That's not enough. So then Cl2 is going to chlorinate. And obviously this Br here, what is that Br? That Br is a weak deactivator. I'm just doing this for you guys. Don't actually do this on the exam. And then NH2 is a strong activator. So since it's a strong activator, it's going to be either ortho or para. And sorry, ortho or para. But we know that this is going to overhalogenate, so it's going to do both. Okay. We have this BR. Ooh, ooh, baby. Baby. Okay. Then we have this. We're almost there. Like, oh my gosh, I'm seeing the lights now. I'm seeing.
The lights.
Okay. Next. So what's the next step? Now that we have this NH2, we need this to go. We needed to get rid of it. How do we get this loud, nagging voice out of this structure? We could use Hono. Do you remember Hono? So we know that with Hono, since it's already since it's already in the NH2 state. If it was NO2, we would have to, hydrate it and whatever. But it's already hydrated for it's an NH2. So we could just go ahead and just go ahead and just put that Hono. For Hono, I usually don't like to make her like different, like along a whole slew of reactions. I like to just put her 1, 2, 3, 4 because it just makes my brain work better. But you could also like do the first step, draw that out with the Hono with the N triple bond and then go to the next step. But doing it this way just makes it easier for you. So do it this way. I'm not sure if he'll make you guys do the Hono, like write it out, but just in case, know it because it's not that terrible to know. So that's Na2, HCl, 0 degrees. Ooh, 0 degrees Celsius. Okay. And our second step. So now that we have that N triple bond N with that lone pair, we can do anything we want. We could add a fluorine, we could add a chlorine, but that's not what the heck we're trying to do here. We're trying to get rid of this gosh darn loud nagging voice. So how do we get rid of that NH2? We have to
poet.
Okay, H3PO2. That's gonna basically like I think hydrate her in some way. Yeah, I don't know.
Focus, focus.
That's good. Hocus pocus. And she's out of here. So yeah, H3PO2 and she's gone. These are like for Hono, Oh
Oh my
my goodness.
gosh. That is really embarrassing.
For Hono, it's really good to know like all the reactions that will give you whatever you want. Like the reaction that'll give you the F, which is I think HBF4, the reaction that'll give you the CL, all those things. Just know all the reactions that follow that Hono step so you can get whatever you need. Because Hono is definitely gonna be a good like whenever you're in need of something, Hono will get you out. So know those final steps. Know those, secondary steps. So now we're done. Yay. CL and CL. There's definitely other ways to do synthesis. That's the beauty of synthesis. You could have another way and it could still work. Definitely, if you have another way, get it checked by somebody before the exam starts. As in like before the exam day. And then if not, yeah. So yep. Because I on my exam I had like 7 steps that was just like not the answer key. I got it marked wrong actually, but then I went to go and advocate for myself and I was right. So advocate for yourself and maybe you were right. And you did a whole slew of things that you didn't have to. You want to go first with the reaction page or should I go?
I don't know, what do you feel
I
like?
want to take a break from talking.
Okay. Well, look at here we are. We're on the last page.
Yeah.
Eh,
Need water.
oh, oh. So now we're here. Oh, let me actually show you the molecule. So we're gonna start on this right side. Is that the right? Yeah, right. And so this is a multi-step reaction, obviously. And so we have our first step here. It's Cl2 FeCO3. Well, what does this do? You might ask. Well, but let's first look at what is on our molecule. So we have what? NO2, obviously, we know by now, NO2 is a strong deactivator. And then our Cl is a weak deactivator. So WD, WID, what are you up to tonight? Like you watching
Alrighty.
this video
Okay.
for real. Anyway, so now
What
based
is
off of
stronger in this case? What are we gonna go by?
we're gonna go by
Goes by
our
patterns.
goes by patterns.
Okay.
So in this case, our CL is our stronger of the two because based on the chart like going up and whatnot. So that means that our CL, because by this reaction, our first reaction, a CL is going to be added, a chlorine is going to be added. So with CL, it's a weak deactivator. That means it's ortho-para-directing. So what positions are those? So that's 1, 2, or 3. Obviously, that para position is blocked, so it can either go here or here, and it can only add in one either or. So I'm only going to draw one of those products because it's actually just the same product, but like flipped, if you will. So what does that look like? Well, that looks like so bang, 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 bang,
Bang,
bang,
bang,
bang,
bang, bang. Yeah.
bang. I'm just feeling myself right
All
now.
right.
Okay. So then we have an H2PD on C, palladium in the works.
Yeah.
Okay. So what does she do? Well, she's actually just going to go ahead and
Go ahead and
just
describe.
hydrate that NO2 group. So now I'm not
Because
going
what
to
is
read.
that? That's Hono. You need to memorize that to know it's to recognize that that's a Hono.
She's the lead up to Hono.
That's part of Hono. That's literally what Hono is. NaNO2 HCl.
I'm
Oh my gosh, I'm
here.
so sorry. Take that all out.
Yeah, you got it. Anyway, what's it called?
So wanted to edit.
No, it won't. It won't because there's only like some places like anyway. So anyway, okay. Well, what's it called? She's gonna hydrate that. So I'm not gonna redraw it. But what this is gonna look like now is just an N. Ooh, I don't really like the way that I wrote that. NH2. Okie dokie. Now our next step that is
Hono!
oh no. So what does that Hono do to the
Target.
NH2? Target. Oh, okay. What's it called? It's just gonna make it's gonna make this a N triple 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 bond N lone pair. That's what she's gonna do. This girly right here, she has a positive charge on her because she has 4 bonds and she don't really like that, but that's just her for now. But now that we have her, and we have this H3O plus, that H3O plus is actually just again, because what does Hono do? She just allows anything to happen.
Not
Wait,
really anything, but whatever is next and she makes
yeah,
sense,
she could
she can
do
do that
it.
for us.
Yeah. So anyway, so what's it called? We have our Cl here, our Cl here, and what does that H3O plus do? Well, it just replaces that N triple bond N with an OH group, and you should know that from your reactions because you've already memorized them at this point. And once again, this is just a benzene. So circle, draw your lines, whatever you feel like. Next, we have this beautiful thingy-mabob right here. What does she do? Well, this is actually just a substitution. Like this is like what we learned back in the day, like
In the day.
like in the day. So as I said, what's it called? That OCH3 is just gonna go ahead and substitute that Cl. And so you're gonna have a final product as such with that OCH3 right there and your CN, she's still right there. Next, we have her now. And so what do we immediately notice? We have a um, strong activator, our OH group right here. And so what does a strong activator do? Well, she's gonna direct again, ortho, meta, para. And so what are our ortho, meta, and para positions here? Well, we have a her and a her and a her. She's not want to go there because she's too busy and whatever and like it'll be too crowded essentially. So she's gonna want to go into the least crowded or the position where there's like least steric hindrance. And then again we can look at our reaction and what is it doing? It's gonna be adding a chlorine. So yeah, we have her right here, OH. Oh, don't forget your literal entire molecule, LOL, like her. And we have our Cl right there. Next, so what do we have here? We have this majiggy, and we have an HNO3, H2SO4. Immediately, she just adds that NO2 right on. Like quite simple, quite, short, sweet, and everything. So,
But how do we know where it adds to?
well, oh yeah, also a great point. Well, how do we know where she adds to? Well, this CH3 right here, that's a war. So she's gonna be a
Weak
weak activator.
activator.
ClCl, she's gonna be a weak deactivator. And so, which one are we going to go based off of? Well, we're going to go based off the weak activator, and the weak activator is going to
Orthopara.
orthopara. So the only open position would be right here because our other two positions are blocked.
The other
So
two,
that,
as in the ortho position.
yeah, the ortho positions are blocked. So what's it called? She's just going to go straight, the NO2 is going to go straight to the para position. So we have CH3, Cl, Cl, and our NO2. Okay. Oh, this one, she's ginormous, gigantrous.
Don't fret, don't fear. Half of that is Hono. You see?
So we're just gonna go throughout all of this like we don't even already know what's up. But if you wanted to, you can just look at this and be like, wait a minute,
Mm.
something's not quite right. But let's just go through the whole thing. Okay. Fuming H2SO4. What does that do? She's gonna add that kind of like blocking group, that SO3H. So I'm
That
just gonna
comes in
draw
handy for
her.
synthesis sometimes, guys. If you ever want to not have the prayer position, you only want to have the ortho, you could block with that fuming H2SO4, which I think you could even have used up there in the past synthesis. Um, but
I'm actually just gonna move this
yeah,
whole
if you
thing
ever
over
wanted to know.
here.
Actually, no, you wouldn't have put the SO3H in the synthesis that was up there because this is a strong deactivator and that would have not overhalogenated for us. So never mind.
Yeah, okay. And then what do we do after HNO3, H2? Oh, wait, let me draw my midget up in there. Okay, what do we do after our HNO3? No, wait, after our H2SO4. So now, again,
No,
we need to,
slow down. It's the recording progress. You need to wait for it to go away and then you talk.
so it's gonna, what's it called? Now we need to recognize again our chart of like priorities and activating and deactivating groups. So SO3, strong deactivator. OH, strong activator immediately. OH, that's what we want to go off of. OH, she's ortho-para-directing. So we have which positions open? Her or her? Yes, we have our ortho positions available.
Because
So
why? Because para is SO3H, not an option.
our HNO3 is going to add NO2 somewhere. So it's going to add obviously that to that ortho position. So we're just going to draw it in one position, but it'd be both. But it's just like the same molecule flipped once again. So we have our NO2 right here. That's our second step. Then we have H3O plus heat. What does that do? Well, I'll tell you. It gets immediately just gets rid of that SO3H. She's gone. She's not
She
relevant
just
anymore.
heated away.
She heated away. What's it called? Now we have our H2PD on C. Again, we have that preface to the HONO. We take off this majigger. We
For
do
hydrating that NO2.
exactly now she's in NH2. What do we do after this step five? Now step
Oh
five, she's
no.
oh no. So now we're gonna make her a N, triple bond, N. Don't forget your lone pairs and your formal charge. But once again, you only need to draw the final product, so
So
she's
that's
actually
now
irrelevant.
exactly good.
Now, step six, we did all of that for what?
What did we
Because
do?
in step six, what do? We just replace that girl with a fluorine.
Yes. And if you didn't memorize the reactions, you might think, what does HBF4 add in HBF? Does it add a B? No, because if you did those reactions, you would know HBF4 after a HONO step adds a what? A fluorine.
A fluorine. And that's all you have. That's
That's
your
not all you
thing.
have.
Wait,
Oh,
you
I thought you were saying for the whole page. What is
no.
it?
What's it called? That's your final product.
We're gonna start. We have this R group up here. Doesn't really matter what kind of R group she is. She's just an R group, okay? And then we're gonna first step it says here is we're gonna brominate. Now, where the heck are we gonna freaking brominate? Where the heck are we gonna freaking brominate? Oh my gosh, wait.
Literally
Okay,
almost done.
so this is an R group. What do we know about R groups? Weak activators. What do we know about weak activators? Ortho para. So this BR, since it's a bromination, is gonna either go here, here, or here. But since this thing is so huge, big, fat, this R group is just so huge, big, fat. We're not going to want to put it at the ortho position. We're going to want to put it at the pair position. So after that first step, he's not asking you to draw every single step through, but I'm doing this for your visualization. Okay? After the first step, your result would be this. But that's not the whole problem. Next, it's a coolie. I call it coolie, but it's actually gamma reagent or organocuprate. So for gamma reagents, what we do with those is we take our halogens and we synthesize. Oh, sorry, so sorry. We substitute it, guys. It's been a long night. We substitute it with whatever's in these parentheses is how I say it. Yeah, and that's what we will put on the structure. So, not on the structure, but we'll be substituting for that halogen. So, we will then CH3, CH3, CH3. So yes. Don't be confused and also put in that two. So put in two CH3s. No. It's only the CH3 that you be putting or substituting in. And then this is our final product, which is the only thing you would have written. You don't need to write this too. And if you do write that on the exam, circle the one that's actually the one that you're referencing. Okay. Next here. If you see something like this, just already know you're gonna have to be writing what's the weak activator. Like literally for all these problems, if you don't know what to do, just write in what it's weak activator or strong activator, whatever, the directingness. So here we have this. This is also huge, big, fat, ugly. It's so huge. This is even huger than one on top. This is huge. This is an R group, which is a weak activator. Oh my. Weak activator. And then that is also another R group. But what do we know about this R group up here? She's so big, fat, big, fat. Guys, we don't fat shame over here. This is only in the cases of carbons and molecules. Okay. All right. So this is a chlorination. And these are both ortho-para directing. So what I'm going to do is I'm going to do it for both of them because they're both weak activators. And you'll see what we go by at the end. But we know that this one is so huge and big and big and big that I'm guessing you wouldn't want to do an ortho-para in comparison to that guy, but we'll see. Okay, let's start with this big fat guy. This is going to be the ortho, and this is going to be the para. Okay. Now for this regular CH3, this is going to be the ortho. This is going to be a para. So in this case, we have all the same options. Yay! In some ways, but now we have to actually use our brain. Now, which one of these is the best option? Because what is the questions asking you? What is the question asking you? It says give one product for each of the following reactions. Okay? Some reactions may give more than one product, but show the best one. So I'm already guessing since this thing is so huge and big, we don't want nothing near her. So boom, two options already removed. We already know that this one is probably the least best option like in the whole entire world because she's trapped between two R groups. So that was terrible. And then this one is just still near that big guy. We don't want her near that big guy. So this is the best option right here. Sorry. This is our best option. So if that was like a question where he asked you which is the H that we want to replace, that would be your answer. You would circle the H on that carbon. If you don't get what I just said, you don't get it. Okay, and that's once again, this is a chlorination, so we're gonna chlorinate at that carbon. Yay! Make sure you draw everything as written. Don't put CH3 parenthesis 3 and miss that first carbon. That one will be marked off. Write it as exactly as it's written. Next, oh my goodness. Is this a blast from the past? Indeed it is. We have BR2 heat. So this is actually going to be from last unit or last exam, like from OCHEM 1. I know, I was thinking that wasn't he. It's like UV. Okay. So is this a blast from the past? Yes, it is a blast from the past. Here we have a bromination, but this V there, I think that's UV. That's going to tell us that we're going to be, I think we're looking for either benzylic or allylic carbons. Those are the things that we're targeting. Now, how do I identify a benzylic or allylic carbon? I'll tell you. What does benzylic or allylic means? Basically, as we see here, this is a benzene ring. Oh, my goodness. This is a benzene ring. Now, in this case, all these carbons that I've just highlighted, they're all contributing to the same like continuous, like, oh my gosh, continuous like electrons in terms of like localization. Like these are all the localized electrons right there. So this is the carbon we're looking at. But we have one carbon that is kind of attached to other things and also this benzene. So we know that one of these carbons is going to be our benzylic carbon. Which one is it going to be? The one that is directly attached to the carbon that is on the ring. Does that make sense? I think it does. So it's going to be the one that's directly attached to the ring that's not in the ring, if that makes sense. So that's the carbon we're looking at. And that BR, that bromination is going to happen right at that carbon. And then in terms of like allylic, what allylic means is like something like that. I'm not gonna do allylic.
Yeah.
I forgot what allylic means, but it's the same thing.
But I think it's
It's like the same thing, but I forgot.
just don't do it.
Yeah.
Yeah, but it's okay.
Okay, so yeah, we're gonna add the BR right to that carbon. Once again, you will not get points off if you do the circle instead of the lines. They mean the same thing. Okay, now what is this NaOCCH3? I don't remember that from any of these flashcards I have for this unit. Why not? Because it was last unit. That is a large, strong base. Yes, don't just throw away all the reactions from last unit. Still have them in your brain. Please. Very important. He might throw 1 or 2 or 3 or 4 on there. So now we have for this carbon right here, what we're looking at. We know we have a large carbon base, so she's going to want to do something with that halogen. How do we determine what is going to happen? Is it going to be elimination or substitution? Well, remember from last unit, This is this carbon right here, or that bromine. The carbon that has the bromine on it has three other things attached. Um, it's a tertiary carbon because it has three carbons attached to it. This is a carbon, this is the carbon, this is the carbon. So that's tertiary. And we have a large strong base there. And what does tertiary do with large strong base? It
Elimination.
eliminates. So we're just gonna get rid of this guy. Yeah, I'm gonna get rid of everything actually. And then we're gonna have a cute little double bond. Doesn't matter which way it goes, it can go on either one. Why? Because it's the same thing. Okay, next. I loved H2CrO4. She's so cutie. If you didn't know, what does she do? She makes a coup. What's a coup? A carboxylic acid, which you will soon learn with IR. But what does H2CrO4 do? I just told you that adds a coup. Now, in this case, what does the coup add on to? It adds on, or it makes an R group a coup. Now, we see here that we have this huge R group, but I think there's something off with this one. What's off with her? Man, she is one, two, three. She got four carbons attached. She's close. She got four carbons attached. She's huge.
Like she can't do. She's already
She
doing too
can't
much.
do,
She
she
got the
doesn't,
weight of her world on her back,
exactly. And
bro.
she also has no age, which we need to do this
Yeah.
reaction. So we actually have no reaction here. So just know that for our H2CrO4, we need this to be, oh my gosh. We can't have her be coordinary. Coordinary carbon?
Just an ordinary girl.
So just know for H2CrO4, we're looking for tertiary carbons and below. Alrighty, so last one here. I know we're all tired. I'm even more tired, guys. It's 11:29 right now. But I just wanted to let you know that. You didn't have to know that. Anyways, we have this phenol, which you should also know because you would have already done what? Your reactions flashcards. Okay, first step is fuming H2SO4. What is fuming H2? Ooh, what does fuming H2SO4 do? She adds to the pair position. She's one of the only things that only does one thing. Why? Because she's just so amazing. Oh. So it's gonna add SO3H. Oh, I should probably write that out on the side. Just an ordinary girl.
And crazy, I get
Okay,
bored.
that's the first step. Second step, we're gonna brominate it. Now, where are we gonna brominate this thing? I have no idea. But oh, wait. OH is a strong activator. SO3H is a strong deactivator. And now we're gonna brominate. But remember when I said before, like strong activators, like they like to over halogenate? Does that apply here? Can I just go ahead and just brominate her on both sides on the ortho position? We can't do that. Why? Because we also have a strong deactivator present. And because of that strong deactivator that is present, um, we cannot over halogenate because she's kind of pulling away from that. She's not making her as active in that way. So it's actually only going to not halogenate. It's only going to brominate in one position. Either here or here, it doesn't matter. They're both the same thing. So the next step, just an ordinary girl. Okay. Next. Nice. So next we have H3O plus heat. What does that do? That's gonna get rid of our SO3H, which you have to know. Know that if you see H2SO4 in your reactions, doesn't matter how far down that H3O plus is with heat, she's gonna get rid of that SO3H as well. So this kind of comes in handy when you want an OH with your Hono. I'm pretty sure when you have Hono, you want an H3O plus. If you did have a SO3H there, I'm pretty sure she would get rid of that as well. So keep that in mind. Alrighty. Right here. Just gonna go ahead and get rid of that buckaroo. And that's our gosh darn answer.
Yay!
Yay! Thank you guys so much for watching. If you have any follow-up questions, we are available via GroupMe, via email, and via our office hours that you guys should come to.
Fridays from
At
2:30 to 3:30 p.m.
yes, indeed. So
Well, good luck on your studying. And once again, this was
dope.
dope.
Dope having you.
Oh my gosh.